In this video, we will examine reactions of alkynes. We will look at electrophilic addition reactions of alkynes, and also we are going to examine some substitution reactions that are specific to terminal alkynes. In a typical electrophilic addition reaction, and one mechanism is shown right here, an intermediate is carbocation. So reaction, for example, of 2-butane with hydrogen bromide would result in formation of vinylic cation as the reaction intermediate, and then that cation would react with bromide anion to give the final product. Now, when we consider stability of carbocations, this mechanism does not appear to be feasible at first glance, and that's because vinylic cation is rather unstable. It's about as stable as primary cation, actually maybe even less stable than primary cation. And as you probably know by now, primary cation is unlikely intermediate in electrophilic additions to alkenes, or at least the reaction proceeds very slowly. So this reaction should not proceed at appreciable rate, simply considering stability of vinylic cation. But actually reaction works very well. It's pretty fast, it works very well, and it's very efficient, gives products in good yield and actually quite cleanly. There are not many byproducts. So this is maybe a little bit unexpected result. The reason for it is that what matters is relative stability, not absolute stability. So in absolute terms, yes, vinylic cation is very unstable, and we would not consider it to be reasonable reaction intermediate, let's say starting with an alkene. That's because to start with, alkenes are quite stable. But alkynes are rather unstable compounds. Their stability is much lower compared to that of alkenes. And being unstable, alkynes have high energy content. And so to convert an alkyne into vinylic cation doesn't take a large amount of energy. So the activation energy is actually not very high. And so even though in absolute terms transition state is higher compared to transition state of corresponding reaction of an alkene, in relative terms, actually energy change is about the same. So conversion of an alkene into secondary cation proceeds actually at about the same rate as conversion of alkyne into vinylic cation. And that's because relative energies of transition states and activation energies are about the same. So as a consequence of high energy content or lower stability of alkynes, these reactions, electrophilic addition reactions of alkynes, work very well. To explain high reactivity of alkynes, an alternative mechanism that does not involve formation of vinylic cation has been proposed. And here is that mechanism shown here on the same example, on example of the same reaction, addition of hydrogen bromide to 2-butane. And the mechanism, as you can see, involves formation of cyclic cation, cyclic 3-membered cation that involves proton electrophile, and then nucleophile attacks from the opposite side to give the product. Formation of trans product or anti-addition of electrophile and nucleophile supports this mechanism. But at the same time, this is also the more stable product, and even from carbocation we would expect formation of the same product. At this point we cannot distinguish between the two mechanisms, and also we haven't been able to observe this intermediate in any other reaction. So for that reason we generally accept mechanism that involves vinylic cation. But you should keep in mind that this is also a plausible mechanism. Yet another reason why alkynes react at such a high rate is that compared to alkenes, there are more collisions that are effective collisions that result in reaction. In case of alkenes, as you can see in this diagram, electrophile has to approach pretty much in the same plane, or approximately the same plane as the pi bond to form a carbon electrophile bond. Obviously it has to interact with pi electron pair. Pi electron pair has to be donated into empty orbital of the electrophile. But as you may recall, alkyne has 2 pairs of pi electrons, 2 pi bonds at 90 degrees to each other. So they form uniform tube of electron density around the carbon-carbon sigma bond. And that means that an electrophile can approach at pretty much any angle, and approach at any angle will result in effective collision and formation of carbon electrophile bond. And then once carbon electrophile bond is formed, the other pi bond that did not participate in reaction, that other pi bond will appear at 90 degrees to the bond that has just formed. Addition of hydrogen halide to an alkene proceeds with Markovnikov rule. That is, if there is possibility for formation of regioisomers. So addition of, again, to use example of hydrogen bromide, addition of hydrogen bromide proceeds in such a way that hydrogen adds to less substitute carbon of the triple bond and nucleophile or bromine to more substitute carbon. Reaction can be carried out with one equivalent of hydrogen bromide, and in this case product is vinylic bromide. And with second equivalent we get dibromide. So note that both bromines end on the same carbon, on the more substitute carbon of the triple bond. And that, of course, is consequence of formation of a more stable carbocation. So addition of first molecule of hydrogen bromide proceeds through more stable vinylic cation, and that would be secondary cation, and then addition of second again proceeds through more stable carbocation, addition of second equivalent of hydrogen bromide. So Markovnikov rule is obeyed. There is also peroxide effect, which means that if we carry out reaction under free radical conditions in the presence of peroxides, here is the mechanism. So then the reaction intermediate is bromide radical, and so bromide radical is the one that first adds to triple bond, not double bond to triple bond, and that results in formation of more stable carbon radical, and that's now more substitute radical. And that results in what we call anti-Markovnikov addition, because bromine ends up on less substitute carbon of the triple bond. So mechanism shows addition of only one equivalent of hydrogen bromide. And here is a reaction that shows addition of one or two equivalents of hydrogen bromide. Again, you will note that both bromine substituents end up on the same carbon atom, but this time they end up on the less substitute carbon atom. So under free radical conditions, regioselectivity is anti-Markovnikov. Halogens, and that is chlorine and bromine, readily add to triple bonds. Fluorine and iodine do not. Fluorine is too reactive, and so reaction cannot be controlled. We cannot get good products. That reaction is too vigorous. On the other hand, iodine is unreactive. So when we say addition of halogens to alkynes, we actually mean addition of chlorine or bromine. And they add, as expected, corresponding to the reactions of alkenes that we have already covered. Since there are 2 degrees of unsaturation, 2 pi bonds, up to 2 equivalents of halogen can add across a triple bond. And that's convenient reaction to distinguish between different types of unsaturations. You know that an unsaturation in an organic molecule could be a pi bond or a ring. In general, rings do not react with halogens. That is, they don't react in the dark. This reaction is carried out in the dark. We cannot carry it out when exposed to light, because light will promote a free radical substitution. We have to avoid free radical substitution reactions. So we carry out reaction in the dark, and usually we carry out reaction with bromine. Bromine is red liquid, and product is colorless product. So disappearance of color of bromine is positive reaction. So here we have example of 1-propyne that reacts with 2 equivalents of bromine, indicating that both degrees of unsaturation are pi bonds. So we have 2 pi bonds. On the other hand, cyclohexene reacts with only 1 equivalent of bromine, which indicates that one unsaturation is pi bond and the other one is a ring. Note that from these reactions we can only tell how many pi bonds and how many rings we have. We cannot tell whether pi bonds are parts of double or triple bond. So for example, in the first case, we can't tell whether we have 1 triple bond or 2 double bonds. And in the second case, we can't say anything about size of the ring, whether it's 5, 6, 7 membered ring. And here is mechanism of reaction. So a cyclic bromonium cation forms as the intermediate, and then backside attack of bromide anion results in formation of final product. So again, addition is anti, and product that is formed is trans. Two bromine, or if chlorine is used, two chlorine substituents end up being trans to each other. There are several methods to add water to an alkyne. Simplest method involves acid catalyzed addition of water. So in such reaction, we simply mix alkyne with water, and sometimes if alkyne is not water soluble, which is usually the case, we may have to add a co-solvent, organic solvent that is miscible with water, such as acetone, or more commonly tetrahydrofuran THF. And then we add a drop of acid as a catalyst, like sulfuric or phosphoric acid. So addition of water proceeds to add one molecule of water across a pi bond in the same manner as addition occurred in case of alkenes. So one pi bond is used up in reaction, the other one remains intact. But product now is what we call an enol. Enol means an alkyl alcohol. It's a compound suffix "in" means alkene and all alcohol. And enols themselves are unstable. So an enol will undergo isomerization, which is called tautomerization. Tautomerization is a specific form of isomerization, and so it will isomerize to keto form. So enol isomerizes into a keto form. Tautomerization is general form of isomerization, and here it is given in general terms using just some letters to indicate hypothetical compound, where we have atoms YZ connected with a double bond. X would be an allylic atom then, attached to Y, and substituent G is attached to X. So tautomerization involves exchange of positions of double bond and substituent G. So substituent G moves to the far atom of the double bond, far relative to itself, so it ends up attached to Z, while double bond now moves to be between atoms X and Y. So whenever we see this isomerization pattern, that's called tautomerization. Here is the mechanism of tautomerization in case of enols. So first step involves protonation of carbon pi bond, and that's accompanied by movement of oxygen electron pair to form carbon-oxygen pi bond. So we end up with oxonium ion. There is no carbocation intermediate. We end up with oxonium ion, and then that oxonium ion in the following step is deprotonated to give keto compound. So that's the stable product. So as a result of addition of water across a triple bond, products are carbonyl compounds, compounds that have carbon-oxygen double bond. Now, acid catalyzed addition of water is not carried out very frequently. Even though reaction is fast and works quite well, it's not very clean. There are a lot of byproducts. It's Markovnikov addition, as well, actually you cannot see that from this example, but if a triple bond is unsymmetrical, addition is Markovnikov, but Markovnikov is not very selective, and we end up with large amount of oxygen being added to less substitute carbon, and so we end up with mixture of products. So even though this reaction works very well, it's not very selective, so we usually carry out addition of water under different conditions. By the way, carbonyl group is carbon-oxygen double bond, and reaction products could be an aldehyde, which means carbonyl group that has one hydrogen attached to it, so one hydrogen is substituent, or both substituents are hydrocarbons. If both substituents are hydrocarbons, then product is a ketone. So you have to be, at this point, you have to be able to distinguish between aldehyde and ketone and classify reaction product as either an aldehyde or as a ketone. Here, reaction product is a ketone. A better method to add water across a triple bond is Oxymercuration-Demercuration. Even though the process utilizes mercury, it is much cleaner, you get single product, and it requires only a catalytic amount of mercury salt. This is a little bit different Oxymercuration-Demercuration reaction compared to one that you have encountered in Oxymercuration-Demercuration alkenes. In this case, we use only a catalytic amount of mercury, use mercuric sulfate as a salt, and we add acid catalyst, sulfuric acid, small amount of sulfuric acid. Also note that demercuration is spontaneous in this case. So unlike oxymercuration-demercuration of alkenes, where we have to carry out separate demercuration step using a reducing agent, sodium borohydride, in this case, demercuration is spontaneous, so we don't have to do anything, we don't have to do another step, it will simply occur in the course of reaction, as you will see from the mechanism. So, in this case, electrophile is mercury 2 plus cation, which is stronger electrophile compared to mercury 1 plus cation. So, mercurium cation adds across a triple bond to end up with this cyclic mercurinium ion. And then addition of water from the opposite side, backside attack, from the opposite side of carbon-mercury bond, results in formation of oxonium ion. So this is oxymercuration reaction. It has been completed at this time. Oxygen and mercury have been added across a pi bond. In the next step, a molecule of water or some other base deprotonates oxonium ion, and we end up with the intermediate that has only positively charged mercury, so one positive charge. Next, protonation of double bond occurs. That's why we need catalytic amount of sulfuric acid. And once double bond is protonated, we end up with carbocation. Carbocation is electron deficient and will attract electron pair from carbon-mercury bonds. It's a very weak bond, and that electron pair is very loosely held by mercury. So mercury cation can easily leave as mercury 2 plus. And that's actually what happens. A carbon-mercury bond is broken. That electron pair flows to form carbon-carbon pi bond, and mercury leaves as mercury 2 plus cation to regenerate the catalyst. So this mercury 2 plus cation can go into first step to catalyze another cycle. As you can see, this is enol form, and here we have abbreviated mechanism shown how a molecule of water removes proton from oxygen and another molecule of water donates proton to carbon-carbon pi bond. That's actually a two-step process, as you have seen a minute ago, and that results in tautomerization to give the product keto form, so stable compound. An alternative way to add water across a triple bond involves hydroboration oxidation sequence, and this method corresponds to one that we have already covered in hydroboration-oxidation of alkenes. So we can use borane as a reagent, for example, a solution of borane in tetrahydrofurane, THF. So here we have reaction of 2-butane with borane, and reaction stoichiometry is 3:1. Obviously, borane has 3 boron-hydrogen bonds, and so each boron-hydrogen bond can be broken to add a boron atom and hydrogen atom across a triple bond. So we end up with trivinyl borane as the reaction intermediate. These reaction intermediates are unstable, highly pyrophoric, they would ignite in air, so we immediately oxidize them with solution of hydrogen peroxide into corresponding vinyl alcohols. As you know, vinyl alcohol is unstable, that's an enol. Vinyl alcohol is type of enol. So this enol now tautomerizes to corresponding ketone. And since we started with 2-butane, we can get only 2-butanone as reaction product. There is no possibility for formation of isomers. So in this case, reaction product is the same as in case of oxymercuration-demercuration, or the same as major product of acid catalyzed addition of water across a triple bond. Now, if alkyne is unsymmetrical, then of course, as you would expect, addition of borane across a pi bond occurs in such a way that boron atom adds to less substitute carbon atom. So we end up with, again, trivinyl borane, and upon oxidation, vinyl alcohol, and then upon tautomerization, an aldehyde. In this case, actually, oxymercuration-demercuration would have given a ketone as a major product. So this is a way to get an alternate regioisomer, so to obtain an aldehyde rather than ketone. There is a problem with this reaction, and that's the triple bond is not sterically very hindered. Triple bond is simply more like a rod, so in terms of shape. So difference between two carbons in terms of steric hindrance, carbon that is substituted with an alkyl group and one that has only hydrogen, is not very large. So for that reason, selectivity is not going to be very good. And even though aldehyde is going to be major reaction product, we'll actually end up with considerable amount of ketone. That's because boron would end up on more substitute carbon atom. Simply, even though boron preferentially adds to less substitute carbon atom, difference between the two is not large enough, and we end up with a mixture of both. So if we want to carry out hydroboration oxidation of unsymmetrical alkyne, we will actually select a different reagent. And that different reagent is dicyanamyl borane. And that's a trivial name for it, and you should know it as that, as dicyanamyl borane. So it's borane that has only one BH bond now, but has two very hindered substituents. Those are so-called cyamyl substituent. Cyamyl comes from secondary isoamyl. So it's abbreviation for secondary isoamyl. It's secondary because carbon bonded to boron is secondary carbon. Iso, note the chain. Carbon next to last has methyl substituents. That makes it iso. And it's amyl. It has 5 carbons. So as you can see, this substituent has been named after corresponding amyl alcohol. And so it's dicyanamyl because it has 2 cyamyl substituents. That makes this boron reagent very hindered. And being very hindered, it's going to add only to less substitute carbon. Because of the high steric hindrance, it's going to make a difference between the two carbon atoms of the triple bond. So even though now there is a small difference between two carbon atoms of the triple bond, one is more, one is less hindered, and one that is less hindered is only slightly less hindered, that's where boron will end up. Because of the high degree of steric hindrance present in dicyanamyl borane, it can add only to less hindered carbon of the triple bond. It will not add to more hindered carbon. Note that there is only one boron-hydrogen bond, so reaction stoichiometry is now 1:1. And we end up with corresponding vinyl borane. Upon oxidation, we end up with corresponding vinyl alcohol. Of course, 2 molecules of cyamyl alcohol are also byproducts, but we are not interested in them. We discard them. Vinyl alcohol, of course, spontaneously tautomerizes into corresponding aldehyde. So this is a method to selectively form aldehydes as only products from terminal alkynes. Alkynes that have carbon-carbon triple bond at the end of the chain. And now we can compare the two methods. So in the middle we have starting material, a terminal alkyne that has carbon-carbon triple bond at the end of the chain. So to the right you have Oxymercuration-Demercuration reaction, and that one results in formation of ketone or metal ketone. So oxygen ends up on more substitute carbon. To the left we have hydroboration oxidation, and you can see that reaction product is aldehyde. So oxygen ends up on less substitute carbon atom. So now we have methods to place oxygen or carbonyl group on either carbon of the triple bond. Just like alkenes, alkynes are readily hydrogenated with hydrogen in the presence of a suitable catalyst. Here are some examples. So, for example, with platinum, hydrogenation goes all the way to alkane. Even though intermediates are alkenes, reaction cannot stop at alkene. And even though alkynes are more reactive towards hydrogenation than alkenes, still these ordinary hydrogenation catalysts are too reactive, and they react quite vigorously both with alkenes and alkynes. So the only products that are isolated are corresponding alkanes, so completely saturated compounds. This reaction is occasionally carried out in part because alkynes are relatively easy to prepare, and so they end up being synthetic intermediates. They're prepared and then converted into end products. If in the second example you can see a molecule contains both an alkene and an alkyne functional group, and both are hydrogenated. And the third example is yet another example. Note that in each of these cases carbon was used as a support. So carbon has no role to play in this reaction. Compounds such as carbon or silica, silicon dioxide, are used as catalyst support. That's because catalysts are generally very expensive, and reaction occurs only in the very top layer of the catalyst. So if we use noble metal as a catalyst, if we use it even as a powder, most of it is wasted because most of the atoms of the metal are inside, on the inside of the catalyst, and there is only very small number of atoms comparatively on the outside in the top layer of that participates in a reaction. So to increase basically the surface area of the catalyst and to better use the catalyst, we apply it in thin layer on a suitable carrier such as carbon or silica. So simply platinum or carbon or palladium or carbon means nothing. Reaction reactivity is the same as platinum or palladium, just that catalyst is cheaper. But a very important reaction is conversion of alkynes into alkenes. And that's very important reaction because alkenes are relatively difficult to prepare, particularly cis alkenes, and they are actually a product of hydrogenation of alkynes, because if you recall the mechanism, two hydrogens add from the same side. So product would be cis alkene. The only problem is that because catalyst is too reactive, reaction doesn't stop with formation of alkene. So to do that, we deactivate catalyst. That's called poisoning of the catalyst. Poisoning is usually undesired reaction because it either reduces or completely eliminates reactivity of the catalyst. But in this case, it is desired. So we add suitable catalytic poison, something that reduces activity of the catalyst. And the best catalyst that can be poisoned is palladium, because it's very reactive, but when we poison it, it's just reactive enough to react with more reactive alkynes, but not reactive enough to react with alkenes. Suitable poisons are aromatic compounds that contain nitrogen. So those would be pyridine, quinoline, or isoquinoline. Also lead acetate has been used as poison. And as I mentioned, since addition of hydrogen is from the same side, then less stable cis alkenes are obtained. And that's very important because cis alkenes being less stable are more difficult to prepare. So this is one really good method, in fact excellent method to prepare cis alkynes. And in the second example, you can see that if alkene function is present elsewhere in the molecule, it will not be affected. Only alkyne, only triple bond reacts. An alternative method to reduce alkynes to alkenes is so-called dissolving metal reduction. In a dissolving metal reduction, we use an active metal, and that's an alkali metal, like lithium, sodium, potassium. We usually use sodium, it's the least expensive and it works very well. And we use ammonia as a solvent. So reaction has to be carried out at low temperature, typically minus 78 degrees Celsius, because under ordinary conditions ammonia is a gas. So we have to liquefy ammonia. That's why we cool it to low temperature. Now ammonia is a liquid. We dissolve alkyne in ammonia, and then we add sodium, which also dissolves and gives dark blue solution. So that's why it's called dissolving metal reduction, because in the course of reaction, metal dissolves. And process is corresponding trans-alkene. So this is a method to make trans-alkenes. Here is the mechanism. So dissolved sodium has one electron, one valence electron. So that electron pairs up with one of the pi electrons to form carbanion. So what that means is that actually electron is donated from sodium and is initially solvated. That's why solution is dark blue. That solvated electron causes pi bond to break homolytic. One electron pairs up with sodium electron to give carbanion, while the other electron ends up on the other carbon of double bond as anion. So the species is both, the intermediate is both carbanion and the free radical. Such species is called radical anion. Radical anion picks up proton from solvent, from ammonia, to give corresponding radical. This is vinylic radical. This vinylic radical will take another electron from sodium, pair up that other electron to give corresponding carbanion. And finally, carbanion is protonated again by ammonia to give corresponding alkene. And as you can see, reaction product is corresponding trans-alkene. The reason why trans-alkene forms is that intermediate carbanion can actually flip, because of the presence of the electron pair, it can flip between cis and trans configuration. And in cis configuration, there is state hindrance between the neighboring substituents. Two substituents are eclipsing. So trans is more stable. So trans carb anion is more stable intermediate. So that's one that forms in the course of reaction, and that's one that is protonated to give then trans alkene. So now when we compare dissolving metal reduction and catalytic hydrogenation, we can see that first reaction, dissolving metal reduction, gives corresponding trans alkene, while catalytic hydrogenation, in the presence of a catalytic poison. By the way, I forgot to mention that poisoned palladium catalyst is called Lindlar catalyst. So sometimes instead of palladium pyridine or palladium quinoline, palladium isoquinoline, you'll simply say hydrogen, or hydrogen / Lindlar or Lindlar catalyst. That means poisoned palladium catalyst. So with poisoned palladium catalyst, product is cis alkene. So now we have a method to convert an alkyne into either trans or cis alkene by choosing suitable reagent. Now, since more stable alkene is result of dissolving metal reduction, sometimes product is cis. So in case of cycloalkynes, the smallest alkyne that can be formed is 8-membered ring, cyclooctane. And in this case, trans double bond actually is not very stable. So the major product would be cis from both reactions, from dissolving metal reduction and catalytic hydrogenation. So the smallest ring that can easily accommodate trans double bond is 10-membered ring. Trans-membered ring could be placed in 8-membered ring, but that's difficult and yield will be low. So 10-membered ring is one where trans double bond can be relatively easily accommodated. So when it comes to cycloalkynes, there's a little bit of an exception, because the minimum size of the ring where trans product will predominate as a result of dissolving metal reduction is 10-membered ring. But for open chain compounds, product is always trans as a result of dissolving metal reduction, and of course in all the cases, cyclic or acyclic, that's open chain compounds, catalytic hydrogenation always gives cis double bond. Now we are going to briefly look at oxidation of alkynes. One common reagent for oxidation of alkynes is permanganate, and we carry out permanganate oxidations either under mild or vigorous conditions. Mild reaction conditions involve permanganate in aqueous solution at room temperature and neutral pH. We actually use a buffer to make sure that pH throughout the reaction remains neutral at 7. Under mild reaction conditions, oxygen adds to each carbon of the triple bond, and final product is dicarbonyl compound, what we call alpha dicarbonyl compound. That means two keto groups are next to each other. So each carbon of the triple bond ends up now with carbonyl group in the product. Vigorous reaction conditions are somewhat more common, and vigorous reaction conditions involve permanganate in basic aqueous solution. So we add sodium hydroxide, reaction solution is basic, and reaction is heated, typically refluxing aqueous solution. In that case, triple bond is cleaved, and each carbon of the triple bond ends up as carboxyl group. So in this case, you can see that triple bond has been cleaved to give monocarboxylic acid on the left and dicarboxylic acid on the right. And you can actually reconstitute where triple bond used to be, where two carboxyl groups now are. An alternative reagent for oxidation of alkynes is ozone. So we can easily carry out ozonization of alkynes. And in the course of ozonization of a triple bond is cleaved, and each carbon of the triple bond ends up as carboxyl group. So you can see that from these three examples. Note that if triple bond is terminal triple bond, so there is only one carbon involved, then that carbon is completely oxidized to carbon dioxide. So that's an exception. Otherwise, carbon of triple bond always ends up as carboxyl group. And note the last example. Last example is cycloalkyne, cyclooctane in this case. So in this case, ring has been opened and we end up with dicarboxylic acid. So If a compound is an open chain compound, triple bond is cleaved to end up with, and so we end up with two products, two separate molecules. But if triple bond is part of a ring, then ring is opened and we end up with single open chain molecule as the reaction product. Finally, we are going to examine substitution reactions of terminal alkynes. Terminal alkynes undergo substitution reactions and as a consequence of their acidity. So first let's review acidity. We covered that in chapter 5. So when we compare hydrides of second row elements like ammonia, water, or hydrogen fluoride, we know that acidity increases in the order of increasing electronegativity of atom bonded to hydrogen. And that can be extrapolated to carbon compounds with respect to hybridization of carbon atom. Because with the increased S character of an orbital, electronegativity of carbon atom increases. So for that reason, acidity of hydrocarbons increases with increased S character of orbital of carbon that is bonded to hydrogen. So sp3 carbon-hydrogen bond is non-acidic. And the same goes for sp2. It is more acidic than sp3 carbon-hydrogen bond, but effectively non-acidic. But on the other hand, sp hybridized carbon-hydrogen bond is rather acidic. Its pKa is 25. And when you compare that with pKa's on the left, you will notice that this compound, acetylene or ethyne, is more acidic than ammonia. You can see that in this diagram. So acetylene is more acidic than ammonia, which means that amide is stronger base than acetylide anion. And we can exploit that in an acid-base reaction. It means that suitable amide, like sodium amide, and sodium amide is stable compound, it's relatively easy to prepare, and can be purchased. It's white powder, comes in a bottle. So we can react any terminal alkyne with an amide, like sodium amide, to produce corresponding acetylide anion. In this case, since spectator ion is sodium, that would have been sodium acetylide, and ammonia is reaction byproduct. Same reaction with hydroxide, like sodium hydroxide, would not work very well because hydroxide is much weaker base, and equilibrium would have been to the left. So now that we know how to prepare acetylide anions, we can use them in synthesis. So acetylide anion is prepared in reaction with sodium amide, and then once sodium acetylide is prepared, it's very strong nucleophile. It can displace leaving group such as halogen, bromine, iodine, even chlorine. In a backside attack, it displaces bromine to form new carbon-carbon bond. So note that in this case, we reacted acetylide anion with bromoethane. And so now it's the ethyl substituent that ends up attached to what used to be acetylide anion. So this is method to prepare internal alkynes from terminal alkynes. Here is another example where substituent is cyclohexyl group, so don't be confused by cyclic substituents. And this is a more common way to represent this sequence. When there is a two-step sequence like this, we use numbers 1 and 2. Under 1, we list first reaction, and then 2 means that after first reaction is finished, we add second reagent. We cannot omit numbers 1 and 2 because it would mean that we mix everything together, and then reaction won't work because lithium amide would have reacted with iodoethane. In this case, I use lithium amide as a reagent. Just use something different from sodium amide, so to understand we don't have to use sodium amide always. It's amide that is important. Counter ion is less important. So lithium amide would generate acetylide anion from the terminal alkyne, and then it would react with iodoethane, and again in this case ethyl substituent would end up attached to terminal carbon of the alkyne. We can react acetylene itself. If we use sodium amide, only monoanion forms, because it's very difficult to remove second proton from something that is already negatively charged, because you'll be removing another positive charge from negatively charged species. So only monoanion forms. And in the next reaction sequence, you can see that we can react sodium amide with acetylene, and here's another reagent, dimethyl sulfate. So we don't need to use alkyl halide. we can use dimethyl sulfate. That one also reacts with electrophiles, and alkyl group, in this case methyl group, will form bond to terminal carbon of the acetylide anion. So in this case you can see carbon methyl group was formed and product is 1-propyne. Now we can carry out reaction at the other end because we still have terminal alkyne. The remaining carbon hydrogen bond is acidic. So we can remove that proton with sodium amide and now react that with this substituent. This is isobutyl group. And now isobutyl group ends up being attached to the other end of the what used to be acetylene. And so now we have placed two different substituents on triple bond. So using this method, we can place two different substituents on triple bond and make a variety of alkynes. And those alkynes are very useful synthetic intermediates. You have seen that alkynes can easily be converted to either cis or trans alkenes, for example. This completes our study of reactions of alkynes, and next we're going to look at a different topic, at stereochemistry.